All right, hey everybody, welcome back to Magnets. Yes, last video we talked about some basics of magnetism, how ferromagnetism works, which is the mechanism behind permanent magnets, and how the magnetic field works. This video we're going to go a little deeper, talk about compasses, Earth's magnetic field, and electromagnetism. So strap in tight, and at the end of the video I have a little surprise for you guys, so I hope you stay till the end of the video. Okay, so we're all familiar with compasses, right? Any Boy Scouts, Girl Scouts, you've seen a compass before. You know that you hold the compass and you turn, and the little needle in the compass always points to Earth's geographic North Pole, right? But have you really thought about how that works? If I handed you a compass and you've never seen one before, it would seem magical to you. The fact that it always knows which direction it wants to be pointing in. The fact that we have a little bit of an introduction to magnetism should give you a clue of how compasses work. So inside of a compass is a needle, and that needle of the compass is a small magnet where the North Pole is clearly labeled in the magnet. So for a lot of compasses, we have a red arrow, which will signify the North Pole. Sometimes there's a little N there, but right now this compass that's on the screen, Earth's geographic North Pole is somewhere between north and northeast. And if we turn, the needle of the magnet will always point to the geographic North Pole. The thing about compasses and how they work, and the mechanism behind compasses actually define how we talk about our field lines. Compasses point in the same direction of magnetic field lines. They point away from the magnetic North Pole and towards the magnetic South Pole. I'm going to say that again. They point away from the magnetic North Pole and towards the magnetic South Pole. Remember that this is a magnet in here. And if this is the North Pole of a magnet, the North Pole of this magnet is not going to want to be attracted to the North Pole of another magnet. It's always going to be pointing towards the South Magnetic Pole. That should kind of give you a clue of what's going on with Earth's magnetic field, but I'm going to go put that off to the side for a second and just strictly talk about compasses. Okay. Now, like I said, when we take a compass, any normal navigation compass, and put it near a magnet, now these bar magnets are going to take over the influence of Earth's magnetic field. The compass will be much more influenced by these bar magnets because there's a much stronger magnetic field near these bar magnets than just having the Earth's magnetic field. The Earth's magnetic field here is negligible, which means we could ignore it. So we said the rule is the compass is always going to point away from the North Pole and towards the South Pole. Your goal, if we have these two bar magnets up on the screen, and I put a compass in any one of these locations, I want you to try to predict which direction the compass is going to point in. Remember the rule, away from north and towards south. Okay, and they always point along the field lines. Last video, we talked about some of the field lines that would be present between these two magnets. Those magnetic field lines, to remind you, always comes out of north and into south. If there's a single bar magnet, it would come out of north into south in these closed loops. So, those arrows of the field lines are defined because of how compasses point. If I put a compass directly between this north and south pole, which way would that compass point? It points along the field lines, away from north towards south. Take a second, try it. I'll wait. Okay. This compass, if I put it here, the compass needle would point towards the magnetic South Pole. Okay, what about this compass needle? If you notice here, this is the same problem that I gave you in the last video. Which direction is the field line pointing at each one of these points? It's the same question as if I put a compass here, which direction is the compass going to point? Well, if we put it towards this South Pole, it follows the field lines, and here the field lines are heading towards the South Pole. What about this guy? I hope that one's next in the animation. What about this one here? Well, field lines come out of the north into the south, so the compass is going to probably want to start pointing towards the South Pole. And that is the direction it points. Now notice here, I was very careful of how I set up this arrow in our animations. this compass is not perfectly between the North and the South Pole. It's kind of off to the side. So that compass needle is not going to point perfectly horizontal. It will be up on that arrow because remember, those field lines loop. And we might still kind of have an upward inflection of the field lines before we head back to the South Pole. If you drew this as perfectly horizontal, that's totally fine. I just kind of wanted to point out that little ambiguity there. But we know that the compass is going to point away from north towards south along the field lines. What about this one? Well, we have a North Pole here. Remember, the compass is a magnet, and that north magnetic pole does not want to be near this north magnetic pole. So something we would do in class, I would give you magnets and I would give you compasses and I would want you to map out the magnetic field around the magnets. And we can use that with compasses. Compasses help us figure out the direction the field lines go. We defined last video that they come out of north into south, and that direction is defined because of our compass. A compass is like a test magnet. What if I put a test magnet there? Which way would the magnetic field out of north into south? All right, but let's revisit compasses and what their use is, right? The compass always points towards Earth's geographic North Pole. So Earth's magnetic field, what's the deal with Earth's magnetic field? Where does it come from? And which end is north and which end is south? You guys are probably aware that Earth is a giant magnet. That's why our compasses work. There's a magnetic field all around Earth. And those compasses always point along the magnetic field lines. But compasses always point to the North Pole. There's a difference between Earth's geographic North Pole and magnetic North Pole. It turns out the geographic North Pole of Earth is actually the magnetic South Pole. The reason why we've probably called it the North Pole is because our compasses are always pointing to the North Pole, right? But our geographic North Pole is actually Earth's magnetic South Pole. Earth is a giant magnet, and the reason why Earth is a giant magnet is because we have charges moving within the molten metals near the core. In earth science, you probably learned about the different layers of Earth, right? We have our crust, we have our mantle, outer core and inner core. And you know that there's a lot of metals towards the core of the Earth. And those convection cells, because of the heat being transferred around the interior of the Earth, makes these molten metals, and these charges start moving around. Well, what's the pure definition of magnetism? Where does magnetism come from? Magnetism comes from, it arises when we have charges moving around. So the complex interaction of Earth's convection cells moving those charges from one place to another creates Earth's magnetic field. Okay, now that sounds like a great explanation, but the actual mechanism behind Earth's magnetic field is still an unsolved mystery. We have an idea of where it comes from, but we're not exactly sure the pure connection between those convection cells and the stable magnetic field around Earth's entire surface. So if one of you guys go into science, some kind of research science, you might be the one that solves the connection between these convection cells and Earth's stable magnetic field. Pretty cool. And once again, something I want to hit home here. Earth's geographic North Pole is actually the magnetic South Pole because our compass needles, the north end points towards the magnetic South Pole. Okay. So take a look. We know that magnetic field lines come in these closed loops, and they come out of the North Pole and into the South Pole. So Earth is a giant magnet where the north end is at the geographic South Pole and the south magnetic end is at the geographic North Pole. Also notice that the spin axis doesn't perfectly match up with where the magnetic South Pole is. They are in two different locations. Earth doesn't perfectly spin around the magnetic point, that magnetic South Pole. Those two locations are actually a little bit different. But our compass needles, they point geographic north, which has to be magnetic south. Isn't that wild? I felt a little lied to when I figured out that fact. Okay. So yeah, great. Earth has a magnetic field, and it helps us navigate in the woods. Real cool. But actually, it turns out that Earth's magnetic field, Earth's magnetosphere, actually protects us from some of the highest dangers out in space. This is a complicated picture. I'm going to try to break it down for you. But we have our sun over here, and we have the Earth over here. Now the sun emits very high energy particles in terms of like solar winds, solar flares. It always is spitting out these high energy radiation out into space. Now, if it wasn't for Earth's magnetic field, life could not exist as we know it on the planet, because not only from the sun, but high energy radiation is always flying around outer space. It's one of the problems that we're actually trying to solve for space travel. When it comes to space travel, we need a way to keep our astronauts and any kind of living organism safe from the high energy radiation out in space when we are outside Earth's protective magnetic field. If we have any high energy radiation or high energy particles coming from the sun, Earth's magnetic field helps deflect some of those particles so we don't get irradiated all the time. Something really wild about Earth's magnetic field is, I said that the geographic North Pole is the magnetic South Pole, but that wasn't always the case. It turns out, due to some evidence that we noticed on the ocean floor, Earth's magnetic field has actually changed poles pretty periodically through Earth's history. The magnetic North and South Pole actually changed sides on the Earth. And when that change takes place, Earth's magnetic field weakens as the poles switch sides. So that could be a potential danger for the future. And it actually turns out that this switching, we said it was periodic, as we saw in some of the ocean floor layers. I don't want to get too into it, but kind of like the direction that some of the metals are pointing in the ocean floor give us evidence that the poles switch sides. Now, when those poles switch, like I said, the magnetic field weakens. And I don't know if you noticed, but in the past 50 years or so, we've really built up Earth's technology around the surface that's protected by the magnetic field. So if that magnetic field starts changing, where it weakens and the poles start switching from one end to another, that could have catastrophic effects on our technology infrastructure. There was actually an incident, I believe it happened in Canada, where there was an intense solar activity that actually caused a lot of technology in Canada to fail. It pierced Earth's magnetic field and really influenced some of the technology infrastructure up there. So, something to keep in mind for the future. Okay. Oh, also, I think it's on my next slide. Let me see. Now, I'm sure you've all have seen pictures or videos of this, but this here is the Northern Lights. Why am I showing you this in a magnetism video? Well, I was talking about Earth's magnetic field. And have you ever really thought about why these Northern Lights occur? Again, if Northern Lights never existed or never knew they existed, and suddenly someone saw these things up in the sky, it would seem like magic. We have these beautiful, colorful wisps in the sky if we go up towards the North Pole. You can actually take cruises that the main goal of the cruise is to see the Northern Lights. But where do they come from? Well, we have Earth's magnetic field. And if you notice here, they come in these closed loops like we talked about. They come out of the magnetic north into the magnetic south. And as they start heading towards the pole, we talked about the magnetic flux density, how those field lines start getting closer and closer together. So these charged particles actually get stuck in Earth's magnetosphere, and they'll start bouncing back and forth inside of these field lines. And as those charged particles from outside in space get caught in the magnetosphere and they start funneling towards the magnetic South Pole, those charged particles start interacting with each other. They start getting close and they start interacting with the molecules in the atmosphere and with each other to create those beautiful colors in the night sky. And the color of the northern lights could actually tell you something about the air composition around this area. If the northern lights look more red, it actually has a higher oxygen content in that area than if they look a little more green like this. Bet you didn't think we were going to be looking at northern lights this video. You were wrong. Okay, the last thing I want to discuss is this idea of electromagnetism. Throughout this topic, where we're talking about electrostatics, circuits, and magnetism, I might have thrown out this word of electromagnetism. But what does it mean? Why do we keep saying this word electromagnetism? We studied electricity, we're studying magnetism. Why do you keep hearing this word electromagnetism? Hopefully by the end of these few slides, you'll see that electricity and magnetism are actually really two sides of the same coin. This is one of the great unifications in physics when we realize that electricity and magnetism actually arise from the same fundamental phenomena. If you took a class in college, you wouldn't take electricity, you wouldn't take magnetism, you take electromagnetism or electricity and magnetism. Okay, so putting that little intro aside, recall that moving charges create a magnetic field. This is the first thing that we said when it comes to magnetism. This was Ørsted's demo. When Ørsted turned on his circuit, we started having current flowing through the circuit. We had moving electrons, and those moving electrons created a magnetic field around the wire. That's why Ørsted's compass started deflecting when the current was turned on. You don't have to know this, but the direction the magnetic field points in when it comes to current carrying wires is actually comes in concentric circles around the wire. Because those magnetic fields always have to be in closed loops. So, you can already see that there's a connection between electricity and magnetism because current is causing a magnetic field to occur. So electric current induces a magnetic field. But what if I just took that loop of wire that I showed you, or that straight wire, and I turned it into a loop? As you can see, let's say we have a current carrying wire that's now in this loop. This closed circular loop changes the magnetic field around the wire. And by getting a closed current carrying loop, we could start to see that it starts to look a bit like a bar magnet, right? Because we said that those magnetic fields come in closed circles around a current carrying wire. So if I take my wire and make it a loop, you can see that we end up with kind of a north pole on this side and a south pole on this side. And if I take this loop and I stack a bunch of very similar loops on top of each other, we get a magnetic field, like I said, very, very similar to a bar magnet. We can often use a coil of wire to create these stacks of current carrying wire. And if you have a stack of wire in a coil, you get a pretty strong magnetic field. And what we call this stack of current carrying wire is an electromagnet. Now, wire is usually made out of copper. Now, copper on its own is not magnetic. That's very important to know. It's not influenced by any kind of magnetic phenomena. But if we take a wire and we coil it up and we have current flowing through it, we now have a magnet. It has nothing to do with the copper itself. It has to do with the fact that electrons can freely move through the copper. And when you have current flowing through the copper, in this coil, in these closed loops, you end up with an electromagnet. And that's a magnet caused by an electric current. Now I'm clicking the date. Okay, you can actually create an electromagnet at home. If you take a nail, any kind of iron nail, you don't even really need a nail, but the nail helps strengthen the electromagnet. And if you take it and you coil the wire around that nail, any nail on your workbench really should be iron, and then we connect it to a battery, you just created a magnet. Now that nail wasn't magnetic, but if we coil some wire around it and shoot it back to the battery, you can now pick up some paper clips with your nail. You set up an electromagnet. And remember, when we have any kind of magnetic phenomena, the magnetic fields come in these closed loops out of the North Pole in to the South Pole. What this diagram is showing you is we have just kind of a standard bar of iron that wasn't magnetic. And we said that when it comes to permanent magnets, those magnetic domains are pointing in the same direction. All of the subatomic motion is acting in the same direction to cause that magnetic phenomena. Those domains are all random when it comes to any kind of standard piece of metal that isn't magnetic, but by setting it up inside of this coil of wire, those domains could start lining up, and then we end up with a magnet. Okay. Now the nice thing about electromagnets, we use electromagnets in our day-to-day lives in a lot of different places. The nice thing about electromagnets is they can be very strong. And not only can they be strong, but we can easily vary the strength of an electromagnet. There's a few ways to do that. It kind of goes beyond the scope of this course and what you guys need to know. But we can change the number of loops inside of the coil to change the strength of the magnetic field. Or we can change the amount of current flowing through that coil. And by quickly just turning a dial and changing the current, we could change the strength of our magnetic field. Another benefit is we could shut off our electromagnet anytime we want. We can't just simply shut off a permanent magnet. So when it comes to electromagnets, they can be easily turned on and turned off, and we could vary the strength. If you've ever been to a junkyard, the things that are picking up the scrap metal are electromagnets. They turn on the magnet when they want to pick up the material, and they turn off the magnet when they want to drop the material. And again, an electromagnet can be made stronger by increasing the current, increasing the number of coils, or inserting a magnetic core into the center of the coil. I said that just a coil of wire will have magnetic properties, but we could put a piece of ferromagnetic material, like we learned about last video, like an iron nail, inside of our coil to increase the strength of the electromagnet. It's a lot of talking. I miss asking you guys questions and have a little bit of a discussion in class, but I guess this will do for now. Okay, so yes, electromagnets exist. We have a coil of wire that has magnetic properties. The current flowing through the wire causes a magnetic phenomena. But let's flip this around the other way. So current can cause magnetism. Moving charges create a magnetic field. But what if, humor me for a second, what if we have this conductor? This red line is a conductor. And it's not connected to any batteries, not connected to anything at all. It is just a conductor. And we take this conductor and we move it through a magnetic field. This kind of flipped the whole discussion on its head. Before, we had current flowing through the wire, and that current caused magnetic properties. But now we have a magnetic field with just any kind of permanent magnetic material. So we have this magnet, and we take this conductor, and we move it through the magnetic field. So now we're changing the magnetic field by cutting it up. If we change a magnetic field, what happens inside the conductor? Well, moving a conductor through a magnetic field creates a potential difference across the conductor. Well, we learned about circuits. If we have a potential difference across the conductor, that causes current to flow. So if we have a conductor that cuts through a magnetic field, moving perpendicular to the field, we get voltage and we get current flowing through the conductor. Now that's really useful to know. I'm gonna fix that. That's really useful to know. So by just taking a conductor, not hooked up to any batteries or anything like that, and just moving it the correct way through a magnetic field, we can get current flowing through that conductor. Okay, so real quick, let's just get some bullet points across and then we'll move on to the next thing. Moving a conductor through a magnetic field induces a potential difference across the conductor. If the conductor is moved parallel to the field, no voltage has to be moved perpendicular to the field. To get maximum potential difference, the conductor must move perfectly perpendicular to the field. And if the conductor is part of a closed loop, current will flow through that conductor. We can make current flow without any connection to a battery. It just has to move the correct way through the magnetic field. Okay, so pausing for a second, I'm getting a little excited, but let's take a look at this question. In a diagram below, in what direction must the conductor be moved to induce the maximum potential difference between its ends? Based on the rules that we saw on the last slide, I have this conductor here. Would I want to move this conductor out of the page, into the page, up, down, left, right? By the way, these little X's tell us that the magnetic field is pointing into the page. We talked about vectors, kind of going off on a tangent here. We talked about vectors, right? Drawing on my screen again, signified by arrows. But what if I wanted a vector that went into the page, this direction? The way we signify that is with these X's. That's the direction the magnetic field is pointing. And if we want to induce the maximum potential difference between its ends, we want to take this conductor and simply move it to the right, chopping those magnetic fields, moving perpendicular to the magnetic field. Magnetic field's going in, and if we have the motion perpendicular this way, right? Into the page this way, we're chopping the magnetic field and we will have a voltage across those ends. So the correct answer is to the right. Okay. I want to put this all together for a second. We're going to do a little thought experiment. So we said that current moving charges create a magnetic field, and changing a magnetic field, like chopping with a conductor, creates current. And if we have current, that means we have some kind of electric field. But something we talked about early in the year is, how do we know really when something's moving? Now, we said at the beginning of the year that we can't really define what's moving unless we have a reference point, right? So let's take a look at this thought experiment here. If I have this coil of wire and a really sensitive ammeter to detect current, that's what ammeters do, and I take this bar magnet and I move it through the coil of wire. Well, by taking this magnet and moving through the coil of wire, we have a magnetic field that's changing throughout the coil of wire. And by changing that magnetic field, we can cause current to start flowing in this loop of wire, right? But that's from the frame of reference of the wire. This is like we're watching the wire moving the magnet. But what if we sat on top of the magnet? Now we're sitting on top of the magnet and the coil is moving over our magnet. So if you ask the wire, the bar magnet's moving and we have a changing magnetic field creating a current. But if you ask the bar magnet, the wire is moving, and that moving wire is creating the current. So this is a really simplified explanation of the fact that whether you're looking at electricity or magnetism depends on your frame of reference. It all depends on who you're asking and who's moving. And that's why there's a fundamental connection between electricity and magnetism. Okay. That explanation, I need to tell you guys, was grossly oversimplified. But I just wanted to let you know that this idea of relativity, what frame of reference you're in and who you're asking plays a very fundamental role in this idea of electromagnetism. The very fact that electricity and magnetism are so linked together. All right. So, current causes magnetism. Moving charges create magnetic fields, and changing magnetic fields create electric fields. We can use that to our advantage, and we do. Okay. This just kind of summarizes everything I just said. A moving charge creates a magnetic field, and a moving magnet creates an electric field. So a better way to say this is a changing electric field creates a magnetic field, and a changing magnetic field creates an electric field. And that means that electricity and magnetism are a result of a single mechanism which we call electromagnetism. You can't talk about electricity without magnetism. You can't talk about magnetism without electricity. They're both two sides of the same coin. Okay. Before I go into some objects or some tools that we use that take advantage of this idea of electromagnetism, something I want to say is you might have learned that light is an electromagnetic wave, right? So even light has a connection with electricity and magnetism. We know light is a wave, so we have a wiggle of the electric field, right? And by wiggling the electric field, by changing the electric field, we change the magnetic field. And this constant changing of the electric and magnetic fields is what causes light to propagate through space. We'll be talking about that a little bit more soon. Okay. A few things I just wanted to show you. We have transformers outside. Transformers use this idea of electromagnetism to change the voltage that's coming out of our sources of electricity when we have like our power plants, right? Power plants are generally coal-fired right now. It means we use coal as an energy source. So we have a certain type of electricity in our power lines outside. And if you look outside your house on a lot of those electric poles, there's kind of like this big box up there. What that big box is an electric transformer. Okay. And what transformers do is it changes the specifications of electricity that's coming out of those power lines. So our AC voltage source would be like our power plants out wherever they are. And those power plants have to transport electricity over an extremely long distance. So we need certain specifications on that electricity in order to go from the power plant to make it to your house. And eventually those power lines get towards your house and we reach our transformer. That electricity reaches the transformer, and that electricity is actually connected to a few closed loops of wire. And our voltage source, we have some closed loops, and it actually heads back out. There's no direct conductive line. There's no direct wire line from the power plant to your house. It has to go through this transformer. And this wire loops around the transformer and heads back. So how do we have any electricity in our house at all if we don't have any direct wire line to the power plant? Well, the way transformers work is we have quite literally a piece of metal inside of the transformer. And we have a certain number of loops in the transformer on this side, and we have a different number of loops on this side. And we said that when we have current flowing through a coil, it creates a magnetic field. That magnetic field transfers through this piece of metal, and then the same magnetic field that's created here gets created here. And by changing the number of loops inside of our transformer, we get different electricity heading into our house, changing the voltage that's actually heading to your computer, cell phone, the voltage coming out of the wall. Okay. That might have been like a lot. But I just kind of want to give you an idea of how these ideas of electricity and magnetism influence the world that we built around you. We also have electric motors. What's the goal of a motor? Well, a motor changes one type of energy into mechanical energy. Your car motor changes the energy stored inside of the gasoline into mechanical energy, which is motion energy, so we can start moving our wheels. An electric motor changes electromagnetic energy into mechanical energy. So the way motors work is we actually have a current flowing through this closed loop of wire within a magnetic field. Now, we said that when we have current flowing through the loop of wire, it creates a magnetic field. And we can create a magnetic field in such a way through this loop of wire that actually starts twisting the wire. So all we have to do is put current through this wire within this magnetic field, and that coil will start rotating, using electricity and magnetism to create motion. This was a really important engineering discovery for us. We knew electricity and magnetism are related, but by actually putting them to work and making changes in our environment, that's the big difference between science and engineering. Science is concerned with the why. Engineering is concerned with the, well, how do we use this to our advantage? We realized that we have current flowing, we could turn the wire, and by having that motion, we could make things work for us, make any kind of electric motors inside of different devices, making changes in the world around us. Now, an electric generator is also important. A generator quite literally generates electrical energy. We could change mechanical energy from our environment into electrical energy. This is how power plants work. They burn coal, spin some turbines, and the spinning of the turbines is what causes electricity to be created, changing that mechanical energy into electrical energy. Generators are quite literally just the opposite of electric motors. So we said that in a motor, we had current flowing through, which turned the wire, which allowed us to make that mechanical energy. But what if we kind of just took that coil and we spun it ourselves? We have this coil of wire that's not hooked up to any batteries or anything like that. It's just a loop of wire. And we take that loop and we start spinning it inside of a magnetic field. By spinning that loop of wire, we actually start creating current that flows through the wire. And this is how these power plants work. Where does that electricity come from? By spinning these loops of wire within a magnetic field, that creates electricity, and we send that to your house. So really the only difference between a generator and a motor is which end are we looking at it from? Are we doing the spinning to create the electrical energy? That's a generator. Or are we sending electrical energy in to make it spin? That would be a motor. Okay. So I really appreciate you guys sticking with me through that whole explanation. I have a treat for you now. I invited somebody on to talk to you a little bit more about how these things work. All right, everybody, I have a treat for you now. We've been talking about electromagnetism, motors, generators. I actually called in a resident expert on the topic. My brother is an engineer at a local engineering firm, and he works very closely with motors, generators, and this whole idea of electromagnetism. I'm going to pull him up on the screen now. He's been waiting this whole time. Hey, Jake.
Going on?
Okay. So Jake, like I said, is works in an engineering firm working with motors and generators. Do you want to talk to us a little bit about what you do first?
Yeah, sure. So I work for a company that sells electronic motors mostly, but other things as well. But I do sort of a lot of project management and customer support with if they have any sort of engineering problems for what the motor would go into. That's something I would help them with.
Awesome. Jake studied physics through college. He was a physics major with an astronomy minor or double major?
No, it was minor.
Okay.
Astronomy minor and a math minor.
Okay, so a physics major, astronomy minor, math minor. And the local engineering firm got him on because of his expertise when it comes to understanding the physics behind how these things work. So Jake, we've been talking about electromagnetism. Do you want to give us a little idea of how electromagnetism plays into how we build our motors and our generators and how we make them do the things we need them to do?
Yeah, so in these motors, a lot of magnetic fields that are induced by electricity. And these magnetic fields, you know how like magnets work, they, repel and they attract. So they use that force to like spin rotors to be able to move things.
Right. So like when it comes to a electric motor, our goal is to turn the electromagnetic energy into mechanical energy. We're trying to make these things move, right? So how does the electromagnetic energy exactly get switched over to mechanical energy? We have a current flowing through the wire, and how does the wire actually end up turning in order to make the motor work?
So the wire induces a magnetic field within the motor, and the stator, or the rotor of the motor, the internals, are magnets as well. So it kind of makes a repulsive force on the magnets, and that causes the rotor to start spinning. And the spinning of the rotor creates torque on whatever you would need to be moved.
Right, and then we could specify how much current is flowing through the motor, what kind of magnets we have in the motor to make the different types of torque that we need. Torque, for those of you who don't know, is the rotational force. These motors actually rotate in order to cause whatever devices we need to work. Now, how does a motor and a generator, how are they related? They seem like two really different things, right? A motor is trying to get something to move. A generator is taking something moving to get electromagnetic energy. So what's the connection between those two?
So every electric motor is also a generator. So you think of an electric motor as you apply a voltage to the motor, and that motor will cause it to spin, obviously. And then, but if you have electrical connection to the motor but with no power running to it, and you spin it by hand or with something else like water or other things, wind, it creates a back voltage out of the motors, and that voltage can be stored, obviously, and then be able to be used to power other things.
So you're telling me that every motor is a generator, and every generator is a motor, it just depends on how we hook it up.
Exactly. You either apply mechanical power to a motor and it creates electrical power, or you apply electrical power to a motor and it creates mechanical power.
Right. So this is actually how we get our electrical energy. That's how these generators work. Like Jake was saying, we could have water spinning a turbine, you have wind spinning a turbine, we could have coal fires to spin some things around, and that's actually how the power plants work near our houses, creating that electrical energy that sends it over to our house.
When there's a blackout and you use a generator, the generator uses a gas motor, and that spins the electric motor to create like a regular voltage that'd be going to your house like a regular power line.
And I don't know about you, but I find this to be like the coolest stuff, because by understanding how these fundamental things work, it gives us not only a better appreciation of the world we built around us and how it works, but as you can see, you could also study physics and get a good job like my brother Jake here. How's quarantine going for you?
All right, a lot of the same. I'm sure everybody is in the same boat, but, just going through day by day, trying to take walks when it's nice out.
Jake's working from home just like all of us on these Zoom calls and everything like that.
It's a lot of fun.
Yeah. But the biggest thing about electromagnetism, I guess, bring it all together, is that electricity and magnetism are so intimately related, right? They're really two sides of the same coin. The fact that we could spin a wire in a magnetic field to get a current, or we could send a current through the wire to spin it in a magnetic field, just shows how closely related electricity and magnetism really are. Exactly. I really appreciate you joining us. Is there anything else you want to say to a whole bunch of high school kids?
I guess good luck with this. I know it sucks, but hey, you got to play with the hand you're dealt, right?
Exactly right. Thank you so much for joining us. I might send questions your way if anyone has any questions about what you do or your expertise.
All right, cool? Sure. I'll take any questions.
All right, great. All right, thanks for joining us. I really appreciate it. That's my brother Jake.
Cool.
I'm so happy that he got to join us today. I'll wrap up the video later. I hope everyone's doing well, and I'll see you in the next video.
All right. Oh, so is this gonna be hard to edit now because of this?
Not at all, dude. Like, that's like one thing I gotta chop. It's all good. I might leave it in. Who knows?
Might leave it in, yeah.